As much fun as the quadratic equation can be, it might be helpful to simplify some of the math. We can do this under certain conditions. So when our equilibrium constant is very small, the position of the equilibrium favors the reactants. We're not going to form much for the products. So if we have a very large initial concentration of the reactants, the reactant concentration will not change much. So with a small equilibrium constant and large initial concentrations, that reactant concentration stays fairly constant when it reaches equilibrium. Because of this, we can assume that the initial concentration remains the same, or approximately the same. We're approximating that the equilibrium concentration is the same as its initial value. This allows us to ignore that subtraction of the change in concentration. Because we're making an approximation, it is good to check to make sure that it is legitimate and able to be made as an approximation. So what we can do is we can compare the value that we've calculated for X to that initial concentration of the reactants. And if we multiply that by 100%, to change it into a percentage, if that value is less than 5%, then we know that we can make that mathematical approximation of ignoring X in the change of our initial concentrations. Let's look at a problem where we can find the equilibrium concentrations using approximations. So let's find the equilibrium concentration of hydrogen and sulfur. Okay. So we're going to start by using the balanced equation as a guide to help to prepare an ice table showing our initial concentrations. So let's start by finding the concentration of our reactants that were given in the problem. So the concentration of H2S is equal to the moles that we initially started with divided by the size of our reaction vessel. So 2.50 times 10 to the -4th molar is the concentration of our reactants, the dihydrogen monosulfide. So now if we look at our balanced chemical reaction, we can build our ice table using the concentrations. Remember, I stands for initial, change, and equilibrium. We know the initial concentration of the H2S. The hydrogen is going to be 0, and the sulfur is going to be 0 because we're starting with just the dihydrogen sulfide. Because of that, we know that our Q is going to be equal to 0 because we only have reactants, we have no products. So our products are 0 divided by the concentration of our reactants, which gives us a Q of 0. Our reaction is going to proceed towards the products or to the right. So let's look at that ice table again. We know that our initial concentration of H2S was 2.50 times 10 to the negative fourth. Our initial concentrations of hydrogen and sulfur were 0. Now we're going to represent the change using X. So our dihydrogen monosulfide is going to decrease because it's a reactant by 2X, 2 because of the coefficient. And our, I forgot a coefficient. Hydrogen is going to increase by 2X because of the coefficient. And sulfur is going to increase by X because the coefficient is 1. Okay, now we can sum each of the columns in order to figure out what our equilibrium concentration is going to be. So we're going to get 2.50 times 10 to the minus fourth minus 2x. 0 plus 2x gives us 2x, and 0 plus x gives us x. And so these are the concentrations that we're going to be using, represented with x, in our equilibrium constant expression. So now we're going to look at our equilibrium constant expression. It is going to be H2 squared, because of the coefficient, S2 over H2S, and that one is also squared because of the coefficient. If we plug in those values from our ICE table, we get 2x squared times x divided by 2.50 times 10 to the minus fourth minus 2x, and that whole value is squared because that's the reactants. So our equilibrium constant is 1.67 times 10 to the minus 7. So we're going to make an approximation to simplify our math. We're going to assume that x is small compared to the initial concentration. So we're going to ignore that 2x to simplify our math and solve this problem. So we have 1.67 times 10 to the minus 7th is equal to 4x cubed divided by 6.25 times 10 to the minus 8th. So I got that from squaring the 2.5 times 10 to the minus 4th. Okay, I'm going to move that 8, the 6.25 times 10 to the 8th to the other side, and then divide by the 4 so that we get our x cubed by itself. And then we can take the cubic root of each side. It's supposed to be a cubic root. And so then x equals 1.38 times 10 to the minus 5th. Now we want to double check our approximation to make sure that this is an appropriate approximation to make. So we're going to take that x value, 1.38 times 10 to the negative 5th. We're going to compare it to the initial concentration, which was 2.5 times 10 to the negative 4th times 100. And if we do that, we see that the value is 5.25%, which is not smaller than 5%. So it's close, but not smaller than 5%. So that means that we cannot make this simplifying approximation. We cannot cancel out that minus 2x. Okay, because our approximation is not valid, there's a couple ways that we can handle this. So we can directly solve using your calculator or by hand this cubic problem, which is a little challenging. Or we have one other option, which is by doing the problem by successive approximations. So what that means is we're going to take that x value that we found and substitute it in for x, solve the problem again, and this should get our answer just a little bit closer. So let's try doing that. So we're going to substitute that value in and solve the problem. I am going to spare you some of the details of solving this. Okay, so once we do that, we find that x is 1.27 times 10 to the minus fifth. So it's a little bit smaller than what we had originally found for x. It should be a little bit closer. Okay. If we substitute it in, we can take this x, substitute it back in for 2x. If we do that again, we find that the answer is 1.28. I shouldn't have a line underneath here, sorry. 1.28 times 10 to the negative fifth, which is nearly identical. And so that means that we've arrived at the best approximation for x. So we can find for H2S, our concentration is going to be 2.5 times 10 to the minus fourth minus 2 times 1.28 times 10 to the minus fifth, which gives us a value of 2.24 times 10 to the minus fourth molar for our equilibrium concentration of H2S. For H2, it's going to be 2 times that value because it was 2x. And our sulfur concentration was just 1x, so 1.28 times 10 to the minus fifth molar. Okay, so we can double check our answer by substituting that calculated value into the equilibrium value. Just to double check to see that we get our equilibrium constant back. And when we do that, we get 1.67 times 10 to the negative seventh. So the calculated value of K is equal to the given value. So therefore, our answer is valid.